Hello students, welcome to my channel. In this course, going to study and delve deeper into the wonders of pre-calculus as a prerequisite to the calculus course. Here, we're going to tackle step by step all the necessary knowledge you need to know before proceeding to higher mathematics. So, let's get started. For my first video, we'll begin with the basics, starting from the real number system as well as proving the properties of real numbers in order to know better how simple algebraic calculations and manipulations work. Let's have a quick recap first. As what we know, the real number system is composed of the set of real numbers, which means it does not include any imaginary value. Mainly, the set of real numbers is composed of two main subsets of numbers, namely, the set of rational numbers and the set of irrational numbers. The set of irrational numbers is composed of all non-terminating, non-repeating numbers. Meanwhile, the set of rational numbers is composed of numbers that can be expressed in the form of p over q, where p and q are integers and q is not equal to 0. Irrational numbers are the opposite of rational numbers because they cannot be expressed as a ratio between two integers. Moving on, the set of rational numbers is a large set itself composed of unions of different subsets. At the most fundamental level, we have the independent element 0, which is neither positive nor negative, and the set of natural numbers or the set of counting numbers starting from 1, 2, 3 and so on. The set of natural numbers is also called as the set of positive integers. The union of 0 and the set of natural numbers is called the set of whole numbers. Opposite to the set of positive integers is the set of negative integers starting from -1, -2, -3 and so on. The union of the set of whole numbers and the set of negative integers are the integers themselves, which can be expressed as the form of p over q, where p is an element of the union of the set of whole numbers and the set of negative integers, and q is strictly equal to 1. So now, let's move on to the properties of real numbers. By definition, the real number system consists of the set of real numbers on which the two operations, addition and multiplication, are defined so that every pair of real numbers has a unique sum and product. This leads us to the field axioms, which governs the manipulative properties of the real numbers. Before we proceed to theses properties, let's start with the field axioms first. We have the closure property for addition and multiplication. This just means that the sum or the product of real numbers is also a real number. Second, we have the commutative property. For addition, the order of two addends does not change its sum. On the other hand, for multiplication, the order of two multipliers does not change its product. Third, we have the associative property, which states that changing the grouping of the numbers does not affect the result of the operation. This means that we can remove or insert parentheses in an expression without changing its value, as long as we only use addition or multiplication. Fourth, we have the distributivity property over addition, which states that multiplying a sum by a number gives the same result as multiplying each addend by the number and then adding the products together. This goes for both left and right-hand approach. Next, we move to the existence of identity elements. For addition, or commonly known as the additive identity, there exists a unique number 0 such that a plus 0 is equal to a. For multiplication, or the multiplicative identity, there exists a unique number 1 such that a times 1 is equal to 1. And lastly, we have the existence of inverses. For addition, known as the additive inverse, there exists a unique number -a for any real number a such that a plus -a is equal to 0. For multiplication, known as the multiplicative inverse, there exists a unique number 1 over a for any real number a such that a times 1 over a is equal to 1. Through the existence of inverses, we derive the operations subtraction and division. Subtraction is the operation that undoes addition, which means to subtract a number from another number, we simply add the additive inverse of that number. Meanwhile, division is the operation that undoes multiplication, which means to divide a number from another number, we simply multiply the multiplicative inverse of that number. These field axioms serve as the foundation of the properties of real numbers. In this section, we will use these field axioms in proving the properties of real numbers to make sense how simple algebraic manipulations work. In this part, we will challenge our fundamental knowledge in algebra on why 4 is equal to the negative of -4. Why -3 times 4 is equal to -12, or multiplying two negatives leads to a positive result. Or why we adhere to the rule that when multiplying two fractions, we multiply its numerators and denominators respectively. We will also delve deeper to the basic properties of adding similar and different fractions, as well as in simplifying complex fractions. First, we will prove the properties of negatives. The first property states that the negative of a is equal to a. First, it is important to note that a proof always starts with a proof word and ends with a tombstone or a small square indicating that a proof is complete. For the proof of the properties of negatives number 1, we already know the concept of additive inverse. So we start with the additive inverse of a. Then we try to get the additive inverse of negative a. Since by definition, the additive inverse of a real number is the negative of that real number, we write that the additive inverse of negative a is the negative of a. To simplify, we rearrange the first equation through commutativity. Notice that the two equations are both equal to 0 and have a common expression which is the negative a. And since the additive inverse of any real number is unique, this must mean that a is equal to the negative of a for the both equations to be equal to 0. Now let's move on to the properties of negatives number 2, which states if a and b are real numbers, negative a times b is equal to a times negative b, which both are also equal to the negative of a times b. To prove, we write the additive inverse of a times b and a respectively. Considering the equation of the additive inverse of a, through the multiplicative property of equality we multiply b from the right. By distributivity property we get the equation a times b plus negative a times b equal to 0. Next we consider the additive inverse of b. Using this equation, we multiply a to both sides of the equation from the left. By distributivity property we get the equation a times b plus a times negative b equal to 0. Using these three equations we have derived in the fact that the additive of the real number a times b is unique, we get this equation. We move on to the properties of negatives number 3, which states that the negative of 1 times a is equal to the negative a. To prove this property, we let the expression negative 1 times a be in the form of negative a times b, which is similar to the properties of negatives number 2, where a is equal to 1 and b is equal to a. By the properties of negatives number 2, negative a times b is equal to the negative of a times b. Substituting the values to the expression the negative of a times b, we get the negative of 1 times a. And since 1 times a is a multiplicative identity, we simplify it to a. Therefore, we arrive at the equation negative 1 times a is equal to negative a through transitivity. Next, let's go the properties of negatives number 4, which states that the product of two negatives, negative a and negative b, is equal to a times b. To prove, first we write the additive inverse of negative a and multiply the equation by b from the right. We get the equation negative a times b plus the negative of negative a times b equal to 0. By associativity, we rearrange the groupings the later expression, forming the equation negative a times b plus negative b times negative a is equal to 0. By properties of negatives number 2 we know that negative a times b is equation to the negative of a times b. Therefore we substitute the expressions forming the equation the negative of a times b plus negative b times negative a is equal to 0. Since we know that the additive inverse of a times b is the negative of a times b and the fact that the additive inverse of any real number is unique and for the both equations to be equal to 0, we surmise that a times b is equal to negative b times negative a. By commutativity, we rearrange the order of the multipliers, thus deriving the properties of negatives number 4. Moving on, let's go to the properties of negatives number 5, which states that the negative of a plus b is equal to negative a minus b. To prove, we incorporate the properties of negatives number 3. Thus by distributivity we get the expression negative 1 times a plus negative 1 times b. Using the same property again, we get the expression negative a plus negative b. Now recall previously that the definition of subtraction mathematically is this. Therefore, the expression negative a plus negative b is equal to negative a minus b. Lastly, the properties of negatives number 6, which states that the negative of a minus b is equal to b minus a. The proof of this property is quite similar to number 5. Here we follow the same pattern, and upon arriving to the expression negative a minus negative b, we incorporate the properties of negatives number 1 to simplify the negative of negative b to b. Next, we substitute the expression, and by commutativity we completed the proof for this property. After proving the properties of negatives, let's move on to the properties of fractions. For the properties of fractions number 1, it states that the fraction a over a is equal to 1. To prove, recall that mathematically the definition of division goes that for any fraction a over b is equal to a times the multiplicative inverse of b. This means that the fraction a over a is equal to a times the multiplicative inverse of a. And since we know that the equation a times the multiplicative inverse of a is equal to 1, we get the equation a over a is equal to 1. Let's move on to the properties of fractions number 2, which states that the product of two multiplicative inverses of different real numbers is equal to the multiplicative inverse of the product of the two real numbers. To prove, we write first the multiplicative inverse of a times b and a respectively, and the properties of fractions number 1 in the form of b over b. By multiplicative identity and a couple of transitivity, we arrive at this equation a times 1 over a times b over b is equal to 1. By definition of division, transitivity and associativity, we arrive at the equation a times b times 1 over a times 1 over b is equal to 1. Finally, using the fact that the multiplicative inverse of any real number is unique, we now completed the proof of this property. Next, we have the properties of fractions number 3, which states that the product of two fractions of the form a over b and c over d respectively is equal to the product of their respective numerators and denominators, such that a over b times c over d is equal to a times c over b times d. To prove, we incorporate the definition of division such that a over b times c over d is equal to a times 1 over b times c times 1 over d. By associativity, we rearrange the expression, and by the properties of fractions, we unify the two fractions into one. Thus, we arrived at the expression a times c times the fraction 1 over b times d, and by definition of division, we completed the proof of the property. Moving on to the properties of fractions number 4, which governs the notion of reducing fractions to its simplest form. To prove, we follow the properties of fractions numbers 3 and 1 to prove the property. Next, let's go to the properties of fractions number 5, which involves complex fractions. This property states that the multiplicative inverse of the multiplicative inverse of a is equal to a. To simplify, we will call it 1 divided by 1 of a. To prove this property, we will use the multiplicative identity in the form a over a to arrive at the equation 1 divided by 1 over a is equal to 1 divided by 1 over a times a. By properties of fractions number 3, we multiply the corresponding numerators and denominators of the two fractions. Since we know that the denominator is of the form of the multiplicative inverse of a, we arrive at the expression 1 times a over 1. Lastly, by properties of fractions numbers 4 and 1, we completed the proof of the property. Let's go to the next property involving complex numbers. To prove, we adapt again the same steps, starting with the multiplicative identity and the properties of fractions numbers 1 in the form d over d and 3 to arrive at the equation a over b divided by c over d times d over d is equal to a over b times d divided by c over d times d. By definition of division and multiplicative inverse of d, we simplify the denominator to century, repeating the same steps again. We use the multiplicative identity and properties of fractions numbers 1 in the form b over b and 3 to arrive at the expression a times 1 over b times d times b over c times b. By associativity, we rearrange b and d, and by the multiplicative inverse of b, we simplify the numerator into a times d, leading to the sole fraction a times d over c times b. We then interchanged c and b, and by properties of fractions number 3, we arrived at the final equation a times d over b times c is equal to a over b times d times c, thus proving the property. Next, we have the properties of fractions number 7, which involves the sum of two fractions of the same denominator. To prove, we start with breaking down the two fractions by definition of division. Through distributivity, we regroup the expression into two multipliers, a plus b and 1 over century. By definition of division again, we transform these two into one fraction, thus proving the property. Lastly, we move to the last property, which involves adding two fractions of different denominator. To prove, let's start with the multiplicative identity and properties of fractions number 1 in the form of b times d over b times d. Substituting the expression by distributivity, then by properties of fractions numbers 3 and 1, we arrive at the expression a over b times d over d plus c over d times b over b. By commutativity, we interchanged c over d and b over b. By properties of fractions number 3, we multiplied the fractions. And then by properties of fractions number 7, we combined these two fractions of the same denominator into one fraction, thus proving the property. And that wraps our first lesson on this video. If you have questions, you can post it on the comment section and I will try to answer them as much as I can. And also, if you have seen any mistake in my discussion, especially in my proofs, kindly point them out for me, since it is always better to learn from each other than on your own. That's it for my first video, students. If this video gets 300 likes, I will immediately proceed to the next topic, which is proving theorems on order. Thank you, and together we struggle and learn in this journey. Subscribe.